An intriguing application of the formula V proportional to R omega relates to the shape of steel wheels that ride on railroad tracks. As in the previous lesson, I'm expressing omega here as RPMs, rotations per minute, which are familiar to most people. Physicists express omega in the unit radians per second, which I won't explain here. When omega is expressed in radians per second and R is in meters, V in meters per second, then the proportion becomes the exact equation V equals R omega. But we'll stick with the RPMs for this lesson. An early problem at the advent of rail transportation was how a train could smoothly follow a curved track. A wheel on the outside of the curve would follow a longer path than a wheel on the inside of the curve. That means the outer wheel would have to move faster than the inner wheel. If not, they'd be scraping and screeching on the curve. But unlike the drive wheels of an automobile that rotate independently of each other by way of gears, the wheels of a train are in one piece, a pair of wheels firmly connected by a rigid axle. This one-piece set of wheels means that the RPMs of each wheel is always the same. Both wheels make the same number of rotations in the same time. Here's where V is proportional to R omega comes into play. Roll a paper cup along the top of a table. Because it's tapered, it rolls in a curve. What's happening is that the wide part has a larger radius. This means the linear speed of the wide part when rolling is greater than the linear speed of the narrow part. Yet both ends, as said, have the same omega. Now fasten a pair of cups at their wide ends, maybe with glue or tape. Then roll them down an incline consisting of a pair of meter sticks. Will they roll off the track? If you try this at home as an experiment, you'll see the answer is no. You'll see that the fastened cups remain on the track and center themselves whenever they roll off center. That's because different parts of the tapered surface have different linear speeds. The greater speed of the wide part of the cup shifts it toward the center. This continual shifting toward the center keeps the cups on the track. And so it is with the wheels of railroad trains. Their rims are tapered. Here's part of an engineering drawing of specs for manufacturing railroad wheels. It's a cross-section of the upper half of the wheel, which clearly shows the taper. Railroad tracks are slightly rounded, so only part of the wheel makes contact with the track. So if the wheel rides on this part, note the radius of the wheel here is slightly greater than here. That means the linear speed is greater on the wider part of the wheel. More speed here than here. The taper and differences in radii are slight, which means the differences in speed are slight. You won't see railroad trains making sharp turns. The rounded part is the flange, which most people think keeps the train on the tracks. Not so. The taper keeps the train on the tracks. If you inspect the flanges next time you're near a train, you'll likely notice that they're rusty. The flanges don't make contact with the track, not in normal operation. Now, if a mishap occurs, a strong hurricane wind, for example, you'll be glad the flanges are there. Let's make a sketch of the set of wheels. Note how the taper is similar to the taper of the fastened cups. So the rims of railroad wheels are akin to tapered paper cups. Let's look at the wheels upon a set of railroad tracks mounted on railroad ties, colored orange-brown here. Like the paper cups on the pair of meter sticks, only part of the wheel surface makes contact with the track. Here we see the wide part of the left wheel on its track, which means the opposite wheel on the right side is on its narrow part. In this position, the left wheel will roll faster than the opposite wheel, what you want to do when making a turn to the right. In practice, the roadway would be banked for such turns, not shown here. Again, note how the wheels relate to the paper cups. Here we see the narrow part of the left wheel on the left track. Can you see the wheels are positioned to make a left-hand turn? Again, we see how the wheels relate to tapered cups. So different speeds for each wheel occur at the same RPMs because each rides in its own different radius. After rounding a curve, a train often oscillates on the straightaway as the wheels self-correct. Take notice of this next time you're riding in a train. This is truly V is proportional to R omega in action. I want to leave you with a question. Back to the pair of fastened cups. If the pair of cups were fastened not at their wide ends, but at their narrow ends, how would motion along the tracks be affected? Think about that. Or better, try it and see. Until next time, good energy.